All right, let's get into the details behind refraction. Now, whenever a wave enters into a new medium, it changes velocity. And I'm going to relate this idea, if you will, just to something you're very familiar with, cars. This is a top view. Cars, and imagine this is mud here. Whenever a car rolls over a new surface, it's going to end up changing speeds just slightly, because some surfaces are more rough, some are more smooth, right? And just because of the coefficient of friction, the car changes speed. Same thing whenever a wave enters into a new substance, a medium, right, the stuff it travels through, it's going to end up changing velocity. Now, whenever it enters into a new medium, because of that change in velocity, if it enters at an angle, the angle is going to end up changing. So now imagine, if you will, a car and some mud. Notice the mud here is at an angle. And the car is driving straight along, and whenever it hits, it actually turns. Reason for that: the tire that's going to end up hitting the first is this front right tire. Now, mud is going to slow it down. Because of that, this tire here, as it drives in, actually begins to drag behind as this tire, who's not in the mud yet, continues forward at a faster speed. Because of that, imagine walking along and then your right shoulder being slowed down as your left shoulder continued at the same speed. That causes a turn into the substance there, or into the normal. Snell's law is this: N2 divided by N1. Now, the N letter here generally represents a refractive index, specifically an optical refractive index, because this is oftentimes done with light, but it works with any wave. Okay, but if you're dealing with light, optical refractive index, N2 divided by N1 equals sine theta 1 divided by sine theta 2, which also is velocity 1 divided by velocity 2. And let me go ahead and point out where these 1s and 2s come from here. If I have, let's take this fish example over here. Those angles are measured from what's called the normal. So let's draw that in. The normal is perpendicular to the surface, and the angles theta 1, theta 2 are measured relative to the normal. So since the light seems to be coming from the fish in this example, which is true, right, it's reflected off, theta 1 is where the light is coming from, and theta 2 is the angle it's going to, all measured relative to the normal, That means substance, this would be in 1, water, which has a refractive index, an optical refractive index about 1.33, and in 2 would be air. And air always has a refractive index of 1. That's the optical refractive index of 1. That's how it's set. So everything that you're going to have as your 1s in this equation here, N1, sine theta 1, V1 is all just the first substance that the light or the sound wave or anything else is going through, and the 2s into sine theta 2, V2 is all the second substance that you are moving into. And once again, whenever it hits at an angle here, right, it's going to end up bending differently. It's going to bend more or less depending on what's happening with the velocities. And this optical refractive index is really a measure of the change in velocities of a light wave as it enters into that. I should also mention, if it goes in straight, there is no change in the angle. I mean, that should make common sense to you, because if you drive a car straight into the mud, right, perpendicular, aka along the normal, there is one wheel doesn't hit first before the other, causing it to turn, because one wheel slows down. It just ends up going straight through. Now, you see examples of refraction all throughout your life. If you put a pencil in water, it actually looks like it's broken just slightly, where it's not. Obviously, it goes straight down, but it looks like whenever it enters the water, it bends. Likewise with fish, your eye thinks the fish is down here, but in reality, the fish is closer to you. If light enters into a block of glass, right, it bends, and as it comes out, it'll bend back there, but almost like it's broken in there, because whenever a wave, whether it's light, sound, or anything else, light's just a common thing to deal with refraction. Whenever it enters into a new medium, if it's entering at an angle, it's going to bend because of the change in velocities. Refraction's also what causes this dispersion effect with light whenever it enters into a new medium. And the reason for that is the refractive index, N2, N1, is actually different for each wavelength of light. So whenever you have different wavelengths, they might bend more or less. One last thing I want to point out is the direction that the wave will bend according to the normal. If you are entering into a medium with a slower wavelength or a slower velocity, the wave will bend towards the normal. Just like this car coming into mud, right? Whenever, if here's my normal, right, I actually bent more towards the normal there. So you're going into a slower velocity, you bend towards the normal. If you were coming from a spot of slower velocity into a higher velocity, like air, if you go back into a spot of higher velocity, you bend away from the normal. So going into slower velocity medium, bend towards the normal. Going into higher velocity medium, bend away from normal. All right, an example problem here for you. I have a person who's very concerned about his fish out in his pond here, and so he goes out at night and shines his flashlight. So we're going to have the light coming from the person to the fish. Shines his flashlight down, and it hits the water with an angle of, let's go 55 degrees. And I want to know, what is theta 2? What angle does it exit what angle does it exit the surface of the water going into the water? Now, this is Snell's Law. You need to pick out of Snell's Law N2 divided by N1 equals sine theta 1 divided by theta 2. So I went ahead and wrote out the entire equation. You need to pick the part of the equation that works for you. I mean, you have three things equal to each other, so you can pick, okay, I want to set these two equal to each other, I want to set these two equal to each other, I want to set these two equal to each other, whichever works best for you. Here it's going to be the optical refractive index, the N2 divided by N1, and our angles, because the optical refractive index of air is always 1, and the optical refractive index of water is always, is approximately, I should say, 1.33, and those are just constants. I don't know if I mentioned this on the last slide, but optical refractive index, or refractive index in general, is a unitless constant. So you just look it up in a table, or it might be the goal to calculate it in a problem. But it's just a constant, unitless there. So I'm going to choose this part of the equation right here. N2 is the stuff we're coming into, right? So here's N2, there's N1. So I got 1.33 divided by 1 equals sine theta 1, the angle that it entered with, sine of 55. Make sure your calculator's in degrees here, because that's what our equation's written in, equals theta 2, so now it's just algebra. And I forgot to write in the sine of theta 2 down here in the bottom, so let me insert that back in. 1.33 divided by 1 is obviously 1.33. And I come out with an angle of 38 degrees, assuming that the optical refractive index of air, that's 1.000, so forth and so on, so I don't have to take sig figs from there, meaning my limiting sig figs here is my input angle theta 1. All right, so another very common problem that you'll see with light, specifically in refraction, I have here a triangular prism. I know the top angle is 40 degrees, and I know the bottom two angles are the same, so 180 minus 40, because 180 degrees in a triangle, minus 40 gives me 140 degrees, and the two angles are, that's how much the two angles at the bottom added up should be, and since they're the same, I know each of these angles down here at the bottom have to be 70 degrees right here. So I put in light going into the prism at a 20-degree angle, and the idea here, the goal behind this problem, is to figure out what is the final angle coming out. So let's think through this problem backwards here for a moment, just try to get an idea. For me to figure out the angle that it's coming out, if I knew this angle right here, then I could use Snell's law to find that final angle coming out. But how to get that angle might be kind of difficult, but check this out. I have here a triangle, and in that triangle I know it has to have 180 degrees. So likewise, if I knew this angle right here, right, there's a 90-degree angle between the two. If I knew this angle, then I could find this angle right here, and which would mean to find that previous angle, I would need this one. Likewise, tracing it back around, I would need that one, and I can figure out that one through Snell's law. So I'm going to go ahead and work that through and explain this problem all the way through again. All right, so I've gone through and I've labeled all those angles that I just talked about. So let's start out finding theta 2 directly across the way, and that's just going to be Snell's law. All right, so I come out with theta 2 to be 13.18 degrees after using Snell's law right here. So N2 is the stuff that the light or any wave is going into, if you will, which is glass here. I told you the refractive index of glass down here, 1.5. And N1 is whatever it's coming from. It's coming from air. Likewise, the 1s and 2s over there solve for theta 2. And I didn't round for sig figs. I'm going to wait till the very end to do that. Now that I have theta 2, let's get theta 3, continuing on my path all the way over here to get the final angle. Notice the right angle that's formed, because this is a normal that I drew in on purpose. This angle is measured to the normal. This angle is measured to the normal, which means 90 degrees minus theta 2 gives me theta 3. Now that I have theta 3, we can calculate theta 4, because here's a triangle, not a right triangle, but still a triangle, and any triangle has 180 degrees in it. And I know the top angle, and now I've got theta 3, that lets me get theta 4. So I come out with an angle for theta 4 of 63.18 degrees. Now that'll let me get over to theta 5, because once again, here's a normal to the surface. That means 90 degrees equals theta 5 plus theta 4, and I know theta 4 now. All right, now to get over to the final angle right over here, I can use Snell's Law. I have the entrance angle coming out of the surface of the glass back into air. So I have the entrance angle. This would be theta 1, which is theta 5, right, actually. And then I'm looking for the final angle, which according to Snell's Law is theta 2, but I'm going to label that correctly. And I'm going from N1 glass into air, right? So once again, the stuff that I'm starting out in now is the glass. That's why N1 is on bottom 1.5, N2 is when I'm going into air, right? And here's the entrance angle, theta 1, and here's the out angle, theta F. And I come out with a final angle of 43 degrees, assuming that I come back in here and I put decimals behind all those initial angles right there, that 40 degrees and that 20 degrees going in. Otherwise, I'd have one sig fig, and that would have to be rounded down to 40 degrees as the angle that the light actually would come out of this prism. One last really fast concept for you. It's this idea of total internal reflection. Now remember from the first slide that whenever a wave comes from a spot of lower velocity into a medium of higher velocity, it bends away from the normal. But eventually, depending upon the, if you're using optical refractive index, but eventually, or velocities, eventually the angle becomes so large, like here, that becomes so large that the refracted angle would actually be 90 degrees or greater, which is impossible. You can't have a refracted angle that goes perfectly along the surface of whatever the medium is, or greater. So at that point in time, this is called the critical angle. Instead, you have reflection that occurs. So whenever you're going from a place like glass into air, water into air, something like that, anytime you're going from a slower velocity to a higher velocity, there is an angle at which it no longer refracts out. It actually reflects in. That's called the critical angle, given by this equation right here. Now, this has many different applications. One of the most obvious applications that's used in our world are optical cables. So we put light in, and it reflects down, always greater than the critical angle, so it never refracts out. So the light stays captured in the cable, and light travels at speed of light. In glass, it's a little bit slower, but it's still approximately 3 times 10 to the 8th meters per second, meaning that the information we're trying to send down the cable can get to its source very quickly, or get to its destination very quickly. I do also want to point out that this equation is actually Snell's Law here. It's just that here's sine theta 1, sine theta 2, or what you're going into, right, actually drops off, because that would be 90 degrees or greater. And sine of 90 degrees, which is where the critical angle takes place, sine of 90 degrees is 1, so anything divided by 1 just drops off. One example problem for you here, I have a scuba diver who is shining a flashlight up at the surface of a water, trying to see something above the water with his flashlight. And my question is, what is the critical angle? So at what point does he keep lowering his flashlight, making the angle greater and greater, or increasing the angle on his flashlight to the surface to where the light no longer actually refracts out, it bounces in? So we're going to use our critical angle equation here. Assuming that air has 3 sig figs, or as many as I need, and this is the limiting factor, significant figures, my critical angle is 48.8 degrees, meaning that any angle at or above 48.8 degrees measured to the normal here will actually, any angle of light that hits there is actually going to reflect off, not refract out, because that's beyond the critical angle. Main mistake made in these problems is just mixing up what N2 and N1 is over here. Remember, N1 is whatever you're coming from. So for critical angle, you actually have to be inside a substance where the speed is less, or if we're talking about optical refractive indexes, your N is greater than the N you're going into, so to speak. So N1 must be larger than N2 for you to have a critical angle. If it's coming the other way, if light's coming down this way, it will always refract every single time. But if you're coming from a spot with a higher optical refractive index into a lower, you can have a critical angle. So just be careful what you put on top of what.